Hey everyone, and welcome. Today we are pulling back the curtain on something that's, well, at the very heart of all computing. We're going to look at how a machine goes from just a boring old string of ones and zeros to actually doing something. We're about to decode the computer's secret language.
So really, how does it all happen? We type on our keyboards, we click with our mouse, we write code, but way down deep inside the hardware, what's actually going on? How does a little piece of silicon know what add or load or compare even means? Well, that is the mystery we're going to unravel right now. Okay, let's just dive right in. It all boils down to a number. For our purposes, it's this 32-bit pattern of ones and zeros. Now we're showing it here in a shorthand called hexadecimal, 0x01ACCC3. But to the computer, it's just a series of tiny electrical signals, either on or off. By itself, it has no meaning at all. So the big question is, how does this blob of bits turn into a specific command?
Well, that whole translation process, it all starts inside a super important part of the CPU, the central processing unit. This is where the magic really begins, where that raw number finally gets deciphered.
I want you to meet the control unit. You can think of it as the director, or maybe the switchboard operator for the whole CPU. It doesn't do any of the math itself. Instead, its one job is to look at the first few bits of our number, a special chunk called the opcode, for operation code. And that opcode, that's the key. Based only on that little code, the control unit fires off a unique pattern of on-off signals to tell the rest of the hardware what to do.
And the process is actually brilliantly simple. It just happens in a few quick steps. First, the CPU fetches our number from memory. Simple enough. Second, the control unit decodes it. It just looks at that opcode part. And third, based on what it sees, its internal logic generates a specific pattern of on or off signals that are going to boss around the rest of the chip. That's it. Fetch, decode, signal.
In this table right here, it's basically the control unit's cheat sheet. A 1 means a wire gets turned on, and a 0 means it stays off. So take a look. For an instruction like XOR, see how the reg-write signal is a 1? That tells a little piece of super fast memory called a register to get ready because it's about to be written to. But for a load instruction, notice how both reg-write and memread are turned on. That's a totally different signal that tells the CPU to go read something from the main system memory. Every single opcode creates its own unique electrical fingerprint.
Okay, so the control unit has sent out all the signals. Now what? Well, now those signals act like little traffic cops, directing the flow of data through the processor's internal highways, what we call the data path. Let's see how that works. So it turns out our number, that 0x01ALCCC3, is actually the machine code for the command XOR S8, S9, S10. Let's trace it together. First, the values that are currently sitting in registers S9 and S10 are read out. Next, those two values get sent over to the ALU, the arithmetic logic unit, which is basically the CPU's calculator. The control signals tell it, hey, you're doing an XOR operation. Finally, that reg-write signal is on, so the result from the ALU gets written back into our destination register S8. And boom, just like that, an instruction gets executed.
We've just seen our number, 0x01ACC33, act like a command. But hang on a second. Here's the question that changes everything, the real mind-bending part of how computers work. Does that string of bits have to be an instruction? And the answer to that is a huge, resounding no. And this right here, this reveals one of the most elegant and powerful ideas in all of computer science. It's not about what the bits are, it's about how they are used. It all, and I mean all, comes down to context.
Get this. This slide shows it perfectly. If the CPU is pointed at a memory location holding 0x01 and CC33 and is told, hey, treat this as an instruction, the control unit decodes it as the XOR command we just saw. But if it's told to treat that same exact pattern of bits as data to be used in a calculation, well, then it's just the number 28,101,683. The bits didn't change at all, but their meaning is completely different.
So here's the bottom line, the one thing you really need to get. Bits are meaningless on their own. Their meaning is assigned to them based entirely on how and when we use them. Is the control unit looking at them? Okay, then they're an instruction. Is the math unit, the ALU, looking at them? Well, then they're just data. Context is everything.
And this idea doesn't just apply to instructions and numbers. The same exact principle is at play when we want to represent something like, well, human language. How on earth do you store an A or a B in a machine that only gets ones and zeros?
This isn't even a new idea exclusive to computers.
Think way back to Morse code, which used shorter patterns for more common letters, or Braille, which used a fixed six-dot pattern. Braille even had these special shift characters that literally told the reader to change the context to start reading the following patterns as numbers instead of letters. This all led to modern standards like ASCII, where we just all agreed that the number 65 represents the letter A. There's nothing special about 65. It's just a convention, an agreement, where context gives the bits their meaning.
Now, as you can probably imagine, if you're a human programmer trying to write an entire program by typing out these long, cryptic binary or hexadecimal numbers well, it's a total nightmare. It's slow, it's tedious, and you're going to make mistakes. We needed a better way.
And so we created the very next layer of abstraction, assembly language. Look at the difference. Instead of that raw machine code on the left, we use these human-readable words. We call them mnemonics, like XR. It's a direct, one-to-one translation, but it's infinitely easier for a person to read, write, and fix when it breaks.
And the tool that builds that bridge for us is called an assembler. It's a pretty straightforward program that does just one thing. It takes that human-friendly assembly code and translates it, line by line, back into the raw machine language that the hardware can actually understand and execute. It's our first, and maybe most important, translator on the journey from human ideas to machine actions.
And that really brings us to our final thought for today. We went from raw, messy binary to a much cleaner assembly language. That's a huge leap in making computers usable. But let's be honest, it's still pretty low level. So what do you think the next layer of abstraction looks like? What's the next step to make it even easier for us humans to tell machines what to do? If you can answer that, you're well on your way to understanding how all modern software is built. Thanks for joining me.